a perfectly good type of initial wave function. So, of course, this n is nothing but a dagger to the nth power. I don't know that. So again, the analogy is that in quantum field theory, you're used to talking about states that look like this. A dagger of some P1, a dagger of some P2, maybe you have a couple of particles, 3 particles in that state, a dagger of some P5. These are the states you know and love already. If there are anharmonic terms, interactions, then you can say you could start with this at some initial time, and you could ask maybe to go to a different state looking very similar, but with different P's and so on, at some later time. And that looks a little bit like a scattering from one set of these states to another set of these states. That's a good question. But there is another kind of question we could ask, which is we could ask about, so all of these things are secretly, just like this is secretly a wave function, meaning this is just some nice notation for the thing that we first learned, which is psi n of x. This picture, okay? These are secretly they're also wave functions, but they're secretly wave functionals, meaning there is some, so this is like an amplitude. I'm in the state called n, and this is the amplitude to be at x. There's something that we almost never talk about, which is the amplitude to be in this. So this is P1, P2 times 3, P5. So there's some name of this state. Usually we make this name. This is P1, P2, 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 P5, right? That's the name of the state. This is the name of this guy's state. And this is a functional of phi space. Okay. In general, this would be if it was a multi-dimensional harmonic oscillator, it would look like that. So while we use this algebra, it's very nice, it's efficient, what it secretly is describing is a wave functional, which says that whatever this quantum field is, it's quantum in the sense that there's some amplitude. If you go and measure it, you can always measure it in, like the relevance of this is if I have a measuring device that measures in x basis, it says where is the particle in x space. It doesn't ask what's your energy, it says where are you in x space. Then this is the amplitude that nth state will be at this position x. This is the amplitude that if I don't measure how many particles there are. That's not the basis I want to work in. I want to measure what is the field doing. You know, some electromagnetic field, there it is. And I'm saying, what is that electromagnetic field? Okay. If I measure that field in that basis, in that sense, then this state has this amplitude for being in this configuration. Where, for example, that could be this. Okay? It's just like x basis is a little irritating to think about when you're thinking about the harmonic oscillator and you're given these nice, beautiful states. Phi basis, field basis, is an irritating thing to think about when you are so used to particle basis, multi-particle basis. This is like multi-occupation number basis, multi-particle basis, particle occupation number. Okay. And so, but it's equivalent. They're just two bases. You know, excitation basis or occupation number basis and position basis are just two perfectly compatible, spanning the same Hilbert space bases. Similarly, there's this thing here. Okay. Now, imagine that you are just thinking of this as some index, just like that is just some index, and this just looks like a wave function and so on. All of this stuff you're used to, now you can see where it fits in. Okay? It fits in simply that this is just some sort of occupation number basis. And occupation number is something we call particle. Okay? It's this packet of energy called particle. Here we just call it occupation number. But secretly, you could say it's all about fields in this way. Okay, I'm running past, I know some people have places to go. So, I hate to start midstream, but this is where we'll take off from. Then I'll try to just link this to, again, what question are we asking? Who is that? Okay. And of course, the question answer is going to be that this is a wave functional like this, which, however, looks horribly peaked at some classical field. Okay, let me say that slower next time. We'll be off and run.